We present WarpMPC, a toolbox for solving large batches of MPC problems on GPU. A common method for solving MPC is via sequential quadratic programming, SQP, where the nonlinear MPC problem is approximated by a quadratic program, QP, to determine a step direction. For large systems that are typical in robotics, the resulting sparse QPs can be efficiently solved with ADMM-style solvers like OSQP, which require one factorization and many backsolves of a sparse linear system. To understand the contributions of this paper, let's first look at how a textbook LDL transpose factorization works. Multiplying out LDL transpose for an element of K gives the equations of the factorization. To find the matrices L and D, we iterate over elements of K and evaluate the arithmetic for each non-zero entry. We unroll operations for all non-zero elements into one program per row of L. To reuse the same GPU kernel, we have to pad operations with zeros to the same length. One contribution of this paper is an optimal partitioning of the rows into multiple kernels that minimizes wasted computations due to this padding. Here we see a segmentation with two kernels in blue, one for row 1 to 5 and one for the last two rows. Similarly, we can unroll the triangular backsolves and directly skip structural zeros. As some rows of L have the same dependencies in the backsolve, we propose executing these in parallel. Here, this is level 1 and 2, which are at the end of the L transpose solve. We fuse the typical tail of levels with a single dependency into one kernel to reduce launch overhead. With our WarpMPC toolbox, we can solve challenging MPC problems, including whole-body MPC for humanoid locomotion. Compared to existing baselines, we can do so for tens of thousands of systems in parallel at high throughput. We illustrate the practical usefulness of WarpMPC by synthesizing a large dataset in simulation and training a neural network approximation of the MPC in under 4 minutes. The resulting policy can be directly deployed on a microcontroller of a crazyfly. The policy commands rotor thrusts and is able to stabilize a nanoquadcopter in hardware experiments. Here we show a sequence of random set points.